Hello, welcome to this session of presentation of inorganic complexes pertaining to the infrared spectroscopy. A huge database for organic molecules in non-IR spectroscopy is present in many books and online resources, but a very few examples are there for inorganic complexes. However, the basics of IR spectroscopy remains the same, that is the selection rule, that is the dipole moment of the molecule. The interpretation of the spectra depends on a few things, such as the substitution of the ligands, back donation from the ligands, pi nature of the ligands, and the charge of the metal atoms, whether it is a transition metal or alkaline metal, or whether it is having a coordinated water system. So this presentation would help you evaluate any inorganic spectroscopy close to the values of the fingerprinting regions that are already mentioned, with some slight deviations. Let's have a look at the selection rules and a few examples in mind.
Hello, this is about infrared spectroscopy of inorganic molecules. To begin with, we shall see the selection rules. As you have seen for the selection rules for the UV spectroscopy, the IR spectroscopy also has a lone and genuine selection rule that says that during the transition there must be change in the dipole moment of the molecule. So if there is a large change, the light molecule interaction is very strong and many photons are absorbed, resulting in large area and intense band. Therefore, we say intense color is there, intense absorption is there if you have a very large dipole band. If there is a small change, interaction is weak and you get a weak color and a weak band. If there is no change, there is no interaction and there is no photon absorbed. So in short, the selection rule tells us which transition gives no change in dipole moment and hence which have zero intensity. The probability when a light shown on the sample is also to be considered, and the light diffraction and absorption also may be taking place. The proportion that is observed depends on the transition probability, and for that probability to get a very good whole number, the nature of the molecule assists. So we shall see a few factors which describe the absorption criteria. For instance, to be absorbed, the light must interact with the molecule, and the oscillating electric field in the light must interact with an oscillating electric field in the molecule. If there is a large change, the light and molecule interaction is strong, as we have seen earlier. And during the transition, there must be a change in the dipole moment. So we'll look into what a dipole moment can contribute, and if there is no change, how it affects the spectra. It can be calculated as the product of charge. As the product of charge, which is given as q times the distance abbreviated between the charges. So it is mu equal to q into r, and the units is the dBi. So a few examples are there. Very good dipole moment is for sodium chloride, and then chloroform, and then for water. Then you have NS3, and there is zero dipole moment for O2 and CCl4. And the answer for this lies that the CO2 and CCl4 are symmetric in nature, and therefore they don't possess any dipole moment. So how do you calculate this? This is mu into q, mu equal to q into r, and this mu is in fact a kind of what you say, a reduced mass, particularly belonging to the nucleons. And this is of the order of 127 pm. You can compare this with the measured value of 1.03 D for HCl. This is a calculated one. The dipole moment of HCl is 1.03 D and the bond length is 127 pm. What is the percentage ionic character? So here is what I told you, 1.160 into 10 power minus 19 C is the charge, and then the R is given as this one, and 1D by this will give you the value of 6.09 D. Actual dipole moment measured for this molecule is 1.03 divided by 6.09, and the percentage come to be about 16.9%. The absorption of energy is here given in terms of the energy levels. These are all small energy levels, and this is one vibrational level and this is another vibrational level, and these are the rotational levels. So any transition from ground state of 1 V0 to another ground state of 1 0 gives a solid line, whereas the transition from one level to another rotational level gives rise to different lines. So these are all again the electronic energy levels. The energy absorbed is different, and these are the vibrational energy levels, and these are the rotational energy levels. A slight comparison is given to the UV visible spectra here, but the energy absorbed is entirely different from the one that you see from rotational lines. The comparison for the Raman versus IR is also given. In the Raman spectra, we have the what is called as the shift, that is the Stokes and anti-Stokes lines that is given there. Either there is increase in the frequency or decrease in the frequency of the absorbed length. But the three major things that define the IR spectroscopy can be given in terms of the bond energy, whether you have a weak bond or a strong bond, or whether you have a triple bond or a double bond or a single bond. So the values are varying. You can see that triple bond is having a very higher value. This is applicable for inorganic system as well. And then the atomic voids. Heavier atoms reduce the wave numbers. For example, you have a very common isotope substitution by deuterium, and it may increase to 3200 centimeter minus 1 in case you substitute with H. So bromine 79, bromine 80 and bromine 81 will simply increase from 550 to 560 to even 600 centimeter minus 1. And this is one of the criteria for finding out whether there is a presentation of a there is an effect of isotopic substitution. And of all this, we need to remember the asymmetric vibration, because most of the time it gives the highest value, that is the frequency nu2. We represent it by nu2. Symmetric stress doesn't produce any change in the dipole moment. Then you have small wagging, twisting, scissoring and rocking moments that you need to take care of, particularly when you have some organic molecules. Some examples are given. The pure asymmetric stretch are coming under 789, 79, 879, 828 and 498. And you can see that this is the new 3, which you have seen here as is a symmetric bending, has got a very good value, and for the calcium carbonate, and that comes to about 1492 to 1429, which with a asymmetric stretch of about 879 as well. This comes to around here. So another example is the bisodium salt of the formate. Here you can see that this is for comparison. Here we have inclusion of a water molecule, which is not very uh, which is not coordinated here in the first example. The second example, it is coordinated, therefore it gives rise to some very broad bands. Because these are the fingerprinting regions, it's very difficult to uh, exactly pinpoint what are the factors. But given the complementary spectra, I can very easily establish the type of atoms there. So here you have MgCO3 and calcium carbonate, which is being compared with an organic molecule. Almost these due to OH, you see the same spectra, but in the fingerprinting region pertaining to the lower wave numbers, you can see a lot of bands there. So here you have something complex because of the CO3 there. Here you have very less CO. Only this is one CO, and this is another. This is another CO, and there is no complexity. Here the complexity is there because of the presence of the double bonds, and because of the presence of the some charges. We are going to see what all this. Again, here is the spectra of aluminum and magnesium hydroxide. This is a superposed one. Almost it's very difficult to identify why this is there, but you can get something very common there, something different. Say peak at 1008 is absent here. Probably in aluminum hydroxide, three OH groups are there. Here you have only two OH groups, and then the CO bonding modes of certain transition metal complexes are given. You can see that it is decreasing and going from 20, manganese, chromium, and vanadium. We're going to see why this thing happens there. In the metal carbonyls, the contribution of the carbonyl stretching is largely dependent on the bridging by the metal-metal bridging, or type of metal-metal bridging, or even if there is any contribution from carbon to the metal or metal to the carbon, as you can see this. So in the intense stretches near 2001 for pertaining to the carbon monoxide CO, which may be terminal or which may be bridge, free CO is a very standard one at 2143 centimeter minus 1. But the presence of some molecular orbitals from the metals change the spectrum pattern. For example, you can see that the metals d bands can overlap with the may overlap in a covalent manner with the carbonyl bands. This is one option. Or the metals d bands can overlap with the pi nature of the, and then that is the pi bond, or the bonds with pi symmetry of the carbonyl complex. So here is a visualized picture of CO, HOMO, and LUMO. In short, LUMO usually is an asymmetric one, which results in most of the time with bondings with pi symmetry. Therefore, the overlapping can assist in transfer of the electron or induction of the electron, therefore resulting in the change in the dipole moment, and therefore ultimately the spectra of the molecule. So here we will see some examples. The CO is some outcome of that. CO stretching wave numbers are shifted to lower values when there are changes in the extent of the back bonding in the compound. Back bonding is usually from metal to ligand. It is not mutual sharing, so sometimes some extra electrons are donated. So the CO stretching wave numbers are shifted to lower values when there is some back bonding with the ground. Removing positive charge from the metal causes the shift of electrons from metal to the CO pi orbitals. That is, if you have a positive charge on the metal and you are compositing it by means of an electron from some sources, or maybe some ligands, the shift of electrons from the metal to the CO pi star orbitals, which are already there, but in a very low density, that causes the CO numbers to decrease. In both cases, we see the decrease. The highest excess of negative charge on the metal occurs in VCO6, as we've seen in the previous table. So more back bonding occurs than in other complexes. So excess negative charge on the metal. Here it is, both are same, almost same. Removing positive charge or introducing negative charge give the same idea. But if already there is a negative charge present on the metal, more back bonding occurs compared to other complexes. That is how you can remove. So the next highest electron density is CrCO6 and then MnCO6 plus. The electron density can be inferred from this particular table with AgCO plus, NiCO4, CoCO4 minus, manganese, chromium, and these complexes. So against the free CO, which is at 2143, you have a very higher CO stretch of about 2204 compared with the very lower stretch of 1860. So that is pertaining to the this particular metal from moving from silver to vanadium. So vanadium, as you've seen that uh, vanadium is seen here, has got some excess negative charge. So it has got a very lowered. Ag is having a very electropositive character, and therefore that particular 0.3 suggests the wave number of about 2204. So ligand donation effect is also there. So you can see the examples, molybdenum complexes. Here you are substituting with PF3, POMe3, PPS3, NCS3 in pyridine, and there is going on reduction from 2090, 1977, 134, 1355. So this suggests that the contribution by ligands is also increasing. This is particularly in that particular order. Electron releasing groups, and finally you have this pyridine, which has got the lowest CO stretch. So a very good generalization that ligand donation as well as metal donation and metal charge affect these things. So CO substitution patterns in chart depends on the positive charge of the metal or the negative electron density and the back donation of electrons from metal to ligand and ligand to metal. So in the end, I'd like to compare it with what we infer from the IR spectroscopy and the Raman spectroscopy. This one is relatively inexpensive, but it cannot be used in aqueous solutions, but there are some developments there. But here in Raman spectroscopy, you can use aqueous solutions, means because it is taking care of the polarizability factor, change in polarizability. It's very easier to identify when in aqueous solution. You usually measure Stokes and anti-Stokes shifts, and the molecule can be used in almost in any state. Here you need a solid sample, pellet KBR, something like that, and the wave numbers that represent IR spectroscopy and Raman spectra are almost the same, but here the nature of the sample that used is differing. Thank you.